So, so welcome everybody. It's a particular pleasure to talk in this session because I think we are at a critical stage in developing modeling technology for society, and unsolved problems are very important. So let me motivate and then make reference to what we have heard so far today. Data science converts data into knowledge and generates value. So in that pipeline, which some of you might have already seen and which goes back to Thomas Fuchs, a PhD student of mine, you start out with hundreds of gigabytes of data, histological slices stained with different techniques or other type of expression data, mass spec data or metabolomics data. You convert them by annotations of doctors into information, and then you condense them into knowledge. This knowledge, in this case, for clear cell renal cell carcinoma, a particularly deadly kidney cancer, it's a broken pathway. And the knowledge then is converted into value. And the value in this particular case is the probability of survival. It makes a difference whether you belong to the prognostically good cohort of green compared to the bad cohort of red. So the point is not that I want to focus on this probability of survival, because some people might put more importance on life quality or other types of values. What I want to point out is that this is a gigantic pipeline for data compression, and it basically has to be modeled in the sense of discriminative learning, estimating posterior distributions. So I'm fully in line with what Jiri was telling us in the first session of modeling posteriors. So what is the problem when you extract value from data? Let me just make 4 different statements. Algorithms that process input with noise compute random variables as output. We know this since Kolmogorov laid out probability theory axioms. What the problem is that when our algorithms return random variables, it's not so clear what it means that the algorithm is correct. So the correctness cannot be determined on the value of a random variable. I have to have a different criterion. So this is something important. The second one is, since Shannon introduced information theory and started the revolution in communication, we know that algorithms, at least decoding algorithms, should compute typical solutions. So the typicality of a solution is certainly related in some way to the correctness of algorithms. Now, in modern times, when algorithms, we do need algorithms that generalize over noise and model mismatch. So this is the generalization issue of modern learning theory. And fourth, and goes back to the grandfather of statistical learning, Wapnick and Jevon-Jenkins. And the last question is, and that relates to what we are doing today, how can algorithms autonomously improve performance? So I think these are the unsolved problem in our field, and some of them are conceptually very deep. Now, let me come back to this pipeline. So in essence, we want to estimate a probability distribution, which depends on all the algorithms involved in the pipeline processing. And this distribution conditions on the data input. So here, these histological slides. And possibly other type of measurements on the patient, as well as the interventions with drugs. You condition on this information and you want to predict the survival probability. At least that's what doctors consider a valuable piece of information for decision making. So my philosophy, or the philosophy I like to follow, is that data science algorithms map uncertain data to uncertain hypotheses. And that means we have to abstract the effect of data science algorithms by a posterior probability distribution. And that's the probability influenced or designed by the algorithms of a hypothesis given data. So that's the framework, and that means we have to now think differently about algorithms and their respective posteriors and how to validate them. So the challenge is what is an appropriate score to optimize, to estimate optimal posteriors. And I will try to motivate an approach here in this short talk. So validation of algorithms, I like to distinguish 3 different levels. The first one is human know how to solve the task, for example, sorting or searching. Then you use algorithms, design and engineering, and there are tons of textbooks how to do that. The second stage is human can solve it, can solve the task, but don't know how. So this is quite often in experience-driven judgment, and then we use supervised learning. Here you see the pipeline, and we have heard this something about this today. And supervised learning means you mimic the human experts. The third stage is human can't solve it at all or not good enough. So we are slowly making progress here. And the first one is autonomous learning by self-play. If the rules of the game are so simple that you can program it, then just program it and let the computer play against itself. And that led to completely new solutions for AlphaGo Zero, but also for new programs for playing chess and other games. The real sort of frontier is unsupervised learning. If no human can tell you how to solve the task, you can just go back and ask yourself, what do we know? And we know a method called the scientific method for generating knowledge, and it has 2 components. On one hand, you want to achieve reproducibility. So when you repeat an experiment, the same conclusions or very similar conclusions should be drawn. And it has to be sufficiently informative. So you need a countermeasure, a balance, and this is provided in terms of information theory. So on one hand, you want to make you want to give a rich answer, and on the other hand, this answer should be reproducible. So how can we now start formalizing these challenge? So let me first give a mathematical framework and then point out a variational approach, how to address these learning of posteriors, and then I show you a short example. So given is a set E of experiments that generate data. So the data depend on the experiments and they come out of some data space. And I deliberately don't want to go into the details what these experiments are. I just need this concept. The goal is you estimate a hypothesis theta out of a hypothesis class depending on the data, and let's use the abbreviation X epsilon as the data for experiment E. So the challenge now is which algorithm A, which maps from the data space to the hypothesis class, should be learned. In particular, if you can't mimic human experts, if you don't have supervision information, this is a tough choice. And in clustering, for example, some people claim that this is not a scientific question, but an art. So I think we have to see how we can make progress on that. There is a richness condition that is sort of the balance to adapting to two simplistic answers. And that says a data science algorithm should use the complete hypothesis class, capital theta, given the full set of experiments. And what I mean by that is that for every hypothesis out of my set of hypotheses, there exists an experiment such that when I use the data of that experiment and I process it by my algorithm, that hypothesis theta must be could be the answer. So if I have a restricted set of experiments and some hypotheses are never used as an answer of my algorithm, then I should throw them away because they are misleading and they are just pretending to give me some richness which is not there. So let's come to the objective for algorithm selection. So I would like to start with the minimum description lengths for posteriors, but I also would like to modify this concept in such a way that it actually captures the notion of generalization. Remember, in unsupervised learning, there was the stability or reproducibility game. And that means if I repeat my experiment, the signal in the experiment is supposed to be the same, but the noise realization is different. So I have to discriminate between signal and noise, but not in the data. I have to discriminate that influence of the data noise on the hypothesis. So the hypothesis is what really matters in these applications. So given a training data X prime of experiment E and test data X double prime of experiment E, I like to use this description length of posterior given test data. And that means we minimize over the algorithmic choices, taking the expectation over X prime, X double prime. We take the expectation over all the hypotheses given my training data X prime. And we evaluate the negative log posterior of these hypotheses, sampled from on the basis of training data, but we evaluate them on the test data. So that I use in the log posterior X double prime the test data, while the hypotheses theta are chosen from the training data. That assures that I measure the bits, the mismatch bits for generalization. Now, this is lower bounded by Jensen's inequality. You know, minus the logarithm is a convex function, so I can pull the expectation into this convex function, and that gives me then minus the logarithm of the expectation of that posterior here. And this term here is a kernel. And I believe that going from this line to this line is a substantial improvement also with respect to rare events. Because, sorry, what am I doing here? Okay. What is the behavior of this term? This term is large when the probability is low. But when the probability is low on test data, this term is also low. So I multiply small probabilities with a large score function, because the minus the log of the probability is large. So you multiply a very small number with a large number. And we know that this is a dangerous game, and you have to hope that L'Hopital actually gives you the right answer. However, if you used Jensen's inequality, you have minus the logarithm of this expectation, and this is essentially a kernel, and this kernel is between 0 and 1. So you ask that the two posteriors agree, and that's essentially the condition here. So this kernel is the sum over all hypotheses, where you take the posterior, evaluate it on the training data and on the test data, and these two posteriors have to agree. So the agreement of posteriors is then the selection criterion. So that was the first part of our optimization problem. The second part was that richness constraint. And so in the richness constraint, what we want to have, we take our posteriors conditioned on data from experiment E, and then we take the expectation over all these experiments. So, and if I have a rich enough set of experiment, my posterior is given then by these what I call the prior weighting, and this should be as similar as possible to the uniform distribution over the hypothesis class. So the second part of this optimization problem is essentially the Kullback-Leibler divergence, between these coverage when I take the expectation over all experiments and the uniform distribution over the hypothesis. And this can be written as the cardinality of the hypothesis class minus the maximum over all algorithmic modifications you consider of the conditional entropy of the hypothesis H given the data X when you take this prior probability. So now you just take these two components, the minimum description length part and this richness constraint. You use the Jensen's inequality to pull that into it. From this term here, we get the entropy. We take the minus sign here and the minus sign of the entropy term, pull it out of the minimum. So we have a maximum here, and that gives us now the maximum criterion for the expectation over the log of the cardinality of the hypothesis class times this kernel. And this is the criterion I like to advocate for model selection when you want to ensure the stability of a posterior under repeated experiments, and at the same time want to make sure that your adaptation of the algorithm is not starting to forget completely about parts of your hypothesis class. Because if you don't pay attention to the richness, then you might converge towards the meaningless answer of null of only one hypothesis, which are given as the answer no matter what the data actually are. So this richness constraint has to balance it, and that is the criterion, which is also which you can also motivate from a information theoretic point of view. So what is the program? Posterior agreement for algorithms validation. First, you employ statistical learning theory. You have to now estimate, since this is depending on the true distribution of the data, the training and the test data. You have to bound it with something which can be evaluated. So you take a sample average over pairs of training test data with that kernel, but then you have to subtract the penalty, and this penalty depends on what kind of algorithmic modification you are considering. Second, you estimate the optimal empirical posterior from this empirical estimate. And then you sample hypothesis theta from that optimal posterior. So these are the three different steps which I advocate to follow. And that gives you then hypotheses which are plausible, informative, and stable. So what is a possible choice for your posterior? I think it's a good starting point to use Gibbs distributions. So you have a set of cost functions which you like, then you write down the Gibbs distributions for them, and then you choose the optimal cost function according to these posteriors agreeing optimally between test and training data. So that's a generic way of taking these concept and fit it into what many people are doing, namely maximum entropy estimation for all kinds of data processing applications. So let me now show you very briefly an example. Cortex parcellation, you go from diffusion weighted images with a diffusion tensor construction and fiber tracking to derive this connectivity matrix, and then you want to group these connectivity matrix so that you can actually color the part of the brain which you want to sort of separate in different areas based on connectivity. This is work by Nico Gorbach. What you will see in the video, which I just start, is then partitioning as a function of the complexity of your pipeline control. So in some sense, what you want to do is, if you like to think in uncertainties, you want to tune the uncertainty of the whole pipeline by allowing more and more complexity. And what you then see is that the informativeness, that's what I call the generalization capacity, is growing. You see more and more structure here coming out. But you also see that you go through from an underfitting stage through that maximum into an overfitting range, and the dashed line are the uncertainty intervals on this curve here. So you have to also see that this is an empirical evaluation of that capacity, because we don't know exactly what the true posterior, what the true score for this posterior agreement is. And at that point, when it stops, it overfitted, and you see it's very fractionated partitioning based on the noise of these areas, and that is not believable in the end. So let me summarize as an outlook. What are these unsolved problems? I pointed out that the correctness of data science algorithms is an open question. So what is typicality in this context? The second point is we have to use regularization. So what is an adequate penalty term for learning algorithms given training and test data pairs? And, it's not good enough that you say, okay, I believe in my cost function, because the cost function is converted, as Jiri also in the first talk pointed out, is converted into a posterior predictor. And as soon as you do that, the posterior has to be normalized. You are changing your cost function. So the conceptual looseness of these strategies become apparent here. And the question is the complexity. How does bounded statistical complexity, and that's what you actually can say from a statistical point of view, influence your computational complexity? And that's what many computer scientists care about, how fast you get the answer. So in summary, I would claim that data science algorithms with all these applications slowly reveal their essence. And I thank you for your attention. And in particular, I also like to give credit to my group for long discussions on these concepts, and I'm open to further discussion.